Hello everyone, we are Group 10 and we are here to discuss our project EEG-based classification and caption retrieval. So the goal was to decode visual reality directly from the brain waves, and the difficulty was huge because EEG data is high dimensional, extremely noisy and non-stationary. Why is this important? The clinical impact is we can use this for restoring communication for patients with locked-in syndrome, and technologically we can build adaptive thought-controlled AR/VR interfaces. Moving on to the data set and data pre-processing, we used EEG image subset from Shui et al., which has visual stimuli, text captions, and EEG recordings. There are trials for 13 subjects over 5 different sessions, and we are particularly focusing on low-speed data for 100 trials. So we have 26,000 total trials. We tried to analyze how the data looks like, and this is what we found for a particular subject. We could identify some patterns which we are trying to use in our model architecture. Coming to the data pre-processing part, we are hard clipping at 500 microvolts to remove extreme muscle artifacts, and we are also applying global standardization for first 3 sessions to preserve relative signal amplitude. We are using session 1, 2, and 3 as training data set. Session 4 is our validation data set, and session 5 is the test data set, and we are also applying cross-session validation in the model.
Okay, so now I'll be talking about the classification architectures that we use for our models. So we started off by using the baseline fully connected model, which we took directly from a paper we referenced. And over here, we could actually observe an accuracy of 10% by our own testing as compared to the papers, which gave 11%. And however, we wanted to actually make this a better model, and we actually tried to make an advanced visual transformer model, which actually takes the input and does linear tokenization by reading all 122 electrode embeddings shots at one time. And then it does positional encoding, passes it to the transformer encoder through self-attention, and uses subject-specific heads. So we treat the 13 different subjects specifically and try to identify patterns in the spikes and noise particular to them as a whole. And via doing this, we could actually see that the peak validation accuracy we achieved was 9.33%. Although this number is actually smaller than what we got through the baseline itself, this could mainly be due to the bottleneck of the signal noise. However, the thing that we noticed is that both the models did double the random choice and random chance as a whole of 5%. The next step we need to do is actually go towards image caption retrieval through the EEG signals. And the way we do this is via using the clip text encoder. And we now pass the EEG encoder that we now train. And we detach the heads of the previous layer. And now we add the new heads so that we can now get both the text encoder and EEG encoder into the same embedding space. And we find the similarity scores between them so that we can train the model better. And the metrics via which we do this are mainly for the classification of the images, we do it via the classification accuracy. And this is done through the loss function of cross entropy. And for the EG caption retrieval, we do it via two metrics, which is recall at K, which measures the correct caption, whether it appears in the top K predictions, and mean average precision, which is the ranking quality with some penalization. And the loss function we use is contrastive alignment and knowledge distillation.
Now coming to the results, we have these results for the task 1, that is classification. So these are the 13 subjects that we have. And as you can see, all the 13 subjects have crossed the threshold of the random chance of 5%. And some of them are also exceeding the expectations and touching around 12% accuracy. Looking at the confusion metrics, we can see that our model was very good at classifying objects like person, flower, and dog. And now coming to the task 2. So we used two strategies for task 2. So the first one was partial unfreezing. So as you can see in this diagram in the right, we have the EEG encoder, which is basically kept unfrozen, which is basically the backbone that we just picked up and plugged into our part 2. So for that, we use new projection heads that was supposed to be trained completely from scratch. So even that was kept unfrozen. And on the other hand, we have the clip model, which had layers 1 and 2, which was kept unfrozen, which was responsible for the embeddings, and rest all the other layers were kept frozen, untouched. So that created a similarity score, and we were getting a recall at 5 of around 17.52%. Then looking at a second strategy, we used LoRa adaptation. So we tried to inject LoRa in our backbone, that is the EEG encoder. So, and rest everything was kept same as the previous strategy. And using that, we trained for less number of epochs, but we got a recall at 5 of around 16.23. So these are the references. These are the papers that we referred for our research. Thank you.